All right, Chemistry 30, welcome to your first lesson about redox. We're going to actually today work on the following outcomes. We're going to define oxidation and reduction operationally, so empirically, looking at observations, and theoretically what's happening with the chemistry behind the scenes. And then we're also going to talk about what an oxidizing agent and a reducing agent is as well. So this is your very first lesson of redox, your basics. This is the most important lesson of the entire chapter. And in fact, the next chapter as well. So if you understand this lesson, then you're in a good place for continuing on. If you struggle with it, you're going to have a hard time. So first of all, what we're actually learning about right now is electrochemistry or redox. And this is the study of reactions involving electron transfer, so electrons moving from one thing to another thing. So some examples of redox reactions. Let's see if I can use my pen here to get this going. So one that's actually shown to the left there is corrosion. I think I spelled that wrong. Another thing would be something like combustion is actually as well a redox reaction. You guys learned in biology when you looked at things like cellular respiration and photosynthesis that electrons are moving around. That also applies. Single replacement reactions, formation, decomposition, all of these are actually examples of redox reactions. In fact, as you're going to learn later on, there are not many reactions that aren't redox, but you're going to learn how to identify in a future lesson which ones are redox reactions and which ones are not. Okay, so I gave more examples than I wrote down here, but just for the sake of time, we're going to keep on moving. So what does redox stand for? Well, redox is actually a combination of two words put together. The red of redox is reduction, which we're going to talk about what that means. And then the ox is oxidation. And we'll talk about what both of those terms mean, both empirically and theoretically. So these terms actually come from metallurgy. So the beginning kind of work of turning ore into pure metals, or the metals actually oxidizing afterwards to go back into ore. That's actually where these terms originally come from. And as a result, there's actually some confusion because you have these empirical kind of terms, these metallurgy terms, and then we learn what's happening behind the scenes. It doesn't really match with the original words, but we'll get into that. So first of all, reduction is the term that's given to turning ore into metal. So again, we're talking about specifically metallurgy here. We're dealing in what we would observe if we were taking ore and actually putting it into metal. If we had a lot of ore, it would turn into less metal because ore is a compound. So I'm dealing with a metal and then like non-metals, right, in ionic compounds. And then the metal is simply the element once I've removed that non-metal. So as a result, I've reduced the amount of material that I have, right, in front of me. Of course, the non-metal material didn't just go away. It's there somewhere, but it's no longer a part of what we're actually looking at. So we reduce the amount we have by turning an ore into the pure metal. So that's kind of the base of this word. So the empirical definition for reduction is the process in which a metal compound is refined into a pure metal. So it's turning a metal compound into a metal element. For example, maybe you take something like iron oxide, right, iron ore, and then you can turn it into pure iron through the process of reduction. In order for reduction to take place, we need a reducing agent, something that causes the reduction to happen. So the reducing agent is a chemical that causes a reduction to take place in another compound. It is the agent for reduction. It allowed it to happen. All right, so we're going to go into chemistry definitions of this soon, but let's take a look at an example. So as an example, if I had something like iron 3 oxide, so this is my ore, it's my compound, and then I reacted it with carbon monoxide, I would get my pure element here. I would get my pure iron. So this is reduction because I went from iron 3 oxide, a larger amount, to iron, the element. So I reduced the amount of iron stuff that I have, right? Don't get this confused with the whole idea of the law of conservation of matter. I didn't lose any atoms. I didn't lose mass between reactants and products. The masses are equal, but when I look at the iron 3 oxide, I had more, right, in terms of mass, and then the iron I have less, so reduction. The reducing agent of carbon monoxide caused the reduction to take place. This needed to be there in order for the iron 3 oxide to get reduced. If the carbon monoxide wasn't there, this would not have happened. So it is the agent for reduction, or the reducing agent is what we call that. Okay, moving on. Oxidation, we're looking at the opposite. And again, we're still in empirical definitions here. This will actually clear up a lot when we get into the theoretical chemistry definitions. So oxidation is the process of a metal reacting to form a metal compound. So it's essentially a pure metal then forming a compound. Does oxygen have to be present? No, it doesn't have to be oxygen that actually is involved in the metal compound in the end. It can be something else. So what is an oxidizing agent? An oxidizing agent is a chemical that helps make oxidation happen. So it is the agent for oxidation. So going forward to actually take a look at an example here, iron rusting is a great one. If I have pure iron and I add oxygen, then I get iron 3 oxide as a product. So iron is my beginning thing that actually gets oxidized, and the agent for the oxidation is the oxygen here itself. It doesn't have to be oxygen. This could be something else, like let's say chlorine. Sure, and that would result obviously in a different product, but that still actually would be an oxidizing agent because it caused iron to turn into a compound. Okay, so that's the metallurgy theoretical definitions that we were looking at. Now let's get into the actual chemistry, the theoretical. No, let's not. Let's first talk about why this is important. Oxidation causes a massive cost to society. So corrosion of cars, pipelines, bridges, and other structures cost an estimated 276 billion US per year, and that's just in the United States. To put this in perspective, that's 76 billion less than the cleanup cost from all the hurricanes of 2005, and that includes Hurricane Katrina. So the economic cost of this is absolutely massive, and that's why we care. I mean, there's a lot of reasons why we care, but that shows you some context for this of how important things like oxidation and reduction is. Later on, we're going to actually talk about how you can prevent oxidation, what kind of technologies we can use to stop it from happening, to prevent that massive cost. All right, theoretical definitions, probably the most important slide of this whole thing. Oxidation is the loss of electrons, and it happens to the reducing agent. Okay, so oxidation is the losing of electrons. This happens to the reducing agent, and this is where it gets a little bit confusing. The agent is like the noun, while oxidation is like the verb, the process. Okay, so oxidation happens to the reducing agent. Reduction is the gain of electrons. So again, this is my verb, right? And it happens to the oxidizing agent. This is my noun, the thing it happens to. So how do I kind of explain this? Let's say that I wanted to give you something. In order for there to be a giving of something, there has to be someone actually doing the giving and then someone taking it, receiving the thing. Those are the agents. So if I am giving a roll of toilet paper, let's keep this thematic. I'm giving a roll of toilet paper. You need to actually be able to accept that. You become the agent for my giving. Okay. In the same way, in order for you to take, right, I am the agent for your taking because I am providing the toilet paper. So when we talk about the agent, we're talking about the chemicals. When we're talking about oxidation and reduction, we're talking about the processes that are happening. So oxidation being like giving and reduction being like taking. Now we're going to clear this up a little bit more. This is your trick for remembering this. Leo the lion says grr. Leo is loss of electrons, is oxidation, and then grr is gain of electrons, is reduction. There's another trick for this that some people like better, so I'm going to actually make a new slide here. Come on, new slide. There we go. And that trick is actually to say instead oil rig. So oxidation is losing and reduction is gaining. Maybe a little bit more Albertan. Yes, to have that oil rig option. So that is another way to remember. Up to you, whether you want to stick with Leo the lion says grr, or if you want to go with oil rig, oxidation is losing, reduction is gaining. Now this just talks about actually the processes, not the agents. There's another kind of trick you can use if you get confused about, oh, which one is the agent, and that's ogre, spelt incorrectly. Oxidizing agent gains, what have I screwed up here? Oxidizing agent gets reduced. I'm sorry, this is a mess. And the problem is actually I don't want to restart this video because if I do, it just will take forever to get to the same spot. So anyways, oxidizing agent gets reduced is what I'm looking at, and that is the trick of ogre, totally something that you can use as well. This slide is really good at kind of showing you how this works. So I've got my two processes, oxidation and reduction. In order for oxidation to happen, I have to have a reduction taking place as well, right? So in order for something to lose electrons, something else has to gain. The electrons can't just disappear. So oxidation, the process, happens to the reducing agent. So the reducing agent is the agent for the reduction of something else, right? It helps it to happen. So the reducing agent goes through oxidation, which means it loses electrons, and as a result, it becomes a little bit more positive than it was before. It had more electrons here, now it has less, right? It lost electrons. In reduction, the oxidizing agent ended up gaining electrons. It was reduced, so it was kind of more positive over here. It gained some electrons, and now it is more negative than it was before. So electrons were gained by the oxidizing agent. So oxidizing agent goes through reduction, gains electrons to become more negative. The reducing agent goes through oxidation, it loses electrons, right, to become more positive. Now, I understand where the confusion is for this. The term reduction, right? Reduction normally means less, that you're getting less than you had before. Not in this case, right? Remember that that definition came from metallurgy, that when we reduced, we had less material in the end of the element than we had of the ore. But reduction in chemistry means you're gaining electrons. You're becoming more negative. This is, I think, the easiest way to think about it. This slide right here is that when you are having reduction taking place, you're going to the more negative. So reduction happens to the oxidizing agent, and as reduction takes place, the thing becomes more negative. That doesn't mean it becomes negative, just more negative than it was before. For example, we could have something like a titanium ion going from a 4 positive charge to a 2 positive charge, and that would be reduction. It became more negative. Well, when I have oxidation, it's losing electrons, so it's becoming more positive. So for example, you could have something like chlorine, right? An atom at 0. Oh, nope, that would be reduction. Joking. Let's say we had something like oxide, O2 minus, that then ends up becoming just an O in O2, right? It went from a 2 negative charge to a 0. So that would be oxidation taking place because I lost electrons. It is becoming more positive. Or maybe I have something like zinc at 0 becoming Zn2 positive. So that is oxidation. It lost electrons. It became more positive. Okay, I'm going to clear actually now all of the ink off of that so I can talk about this. Let's use the eraser. No, my shortcuts are not working as I wanted. All right, there we go. Let's get rid of that. All right, so now let's go back to talking about kind of my memory trick for this. If I'm getting more negative, that's reduction. And I know this is going to sound ridiculous, but in my head I go ner as in negative reduction. This one maybe works a little bit better. As something is becoming more positive, that's oxidation. So poo, yeah, it's funny because it's bathroom humor. So oxidation is occurring. I'm becoming more positive. So again, if it's becoming more negative, it's going to the negative side, or just getting to a more negative charge than we had before. That's ner, it's reduction. If I'm going to a more positive charge, it becomes more positive than it was before. That's poo, it's oxidation. And again, reduction happens to the oxidizing agent, oxidation happens to the reducing agent. All right. So saying the same thing, more negative means reduction, more positive means oxidation. So now let's actually go through some examples and you can see what I mean by all of this. And we'll talk about the oxidation that's happening, the reduction, all that jazz. Now, when we start this, we don't have all the tools yet in order to be able to figure out charge and stuff. So just kind of go with what I say here in terms of what the charges are on things. Later on, you're going to use a tool called oxidation numbers that you can use to determine what the charge is on everything. We don't have that yet. So we're just kind of talking about elements and ions, elements having 0 for a charge and ions having the charge that they would have in the ionic compound. So to start off, if I take a look at my normal reactant silver I have here, that has a charge of 0. It's an element. It doesn't have a charge. Chlorine would also be a charge of 0 here. So silver goes from 0 to having a positive 1 charge when I look at silver chloride, right? Silver in an ionic compound is positive 1, while chloride would end up being negative 1. So when I take a look at what process happened, silver went from 0 to positive 1. It became more positive, so this is oxidation. Poo! Yes, more positive, oxidation. When I look at chlorine, it went from 0 to having a charge of negative 1. So this ner, it reduced. It's reduction. Okay, more negative, reduction, hence the ner. So oxidation happens to the reducing agent. So silver, and now I'm not talking about a process, right? This is the arrow of showing the process happening to silver. Now I'm talking about what silver is. Silver is the reducing agent. So, oh, that was a weird eye. So this is the thing that actually helped chlorine to reduce. It was the agent for chlorine's reduction. Well, chlorine is the oxidizing agent. So chlorine was reduced, right? And by doing that, it was the agent for silver's oxidation. So chlorine is the oxidizing agent, silver is the reducing agent. Silver went through oxidation and chlorine went through reduction. When we're talking about agents, we're normally talking about reactants. Okay, so we're labeling the reactants as either the oxidizing agent or the reducing agent. Think for a second, can you have an oxidizing agent without there being a reducing agent? Pause, you're thinking. No, you cannot. You cannot have a giver without a taker, right? You need to have a oxidizing agent in order for there to be a reducing agent. Both processes have to take place, which means you have to have both agents present. All right, here's another example. I've got chlorine and sodium reacting to make sodium chloride. I have this aqueous, and the reason why I have this aqueous is so that we can treat it as separate ions because it associates in solution. So if I take a look at chlorine, this would be a 0, right, because it's an element, right, so it doesn't have a charge. Sodium would be 0, and then in sodium chloride, I have a positive 1 and a negative 1. So chlorine, and I'm going to try really hard to draw a decent arrow. Oh, it's bad. It's bad, but oh well. Chlorine goes from 0 to negative 1, so it's becoming more negative than it was. So this is going through reduction. In other words, it gained negative electrons, right? It GERD. Well, sodium went from 0 to positive 1, so this became more positive. It pooed. It's oxidation. So it became more positive, it's oxidation. And this happened because it lost electrons, right? It lost negative things, so it became more positive. It's oxidation. So chlorine itself would actually be labeled as the oxidizing agent, right? For short, we call this the OA. And it's the oxidizing agent because it was the agent for sodium's oxidation. Without chlorine, that could not have oxidized. Well, sodium is the reducing agent. So it is the agent for the reduction of chlorine. So this is the reducing agent. All right, so that is that example. Here is one more. Now, what I would actually have you do, and probably should have done this for the last one as well, is that you should actually just pause this, try it out on a piece of paper, and then once you've done trying it out, come back and see if you're right. So pause now. All right, here's the solution. So if I take a look at iron 3 nitrate, iron 3 would have a 3 positive charge. Aluminum would have a charge of 0. Nitrate actually is going to be treated as a spectator ion, so we're not going to talk about that or worry about it, which could have been maybe something that was a bit of a roadblock for you trying out this example. But nitrate, as you know, altogether would have a -1 charge. Later on, we're going to learn how to split up those different atoms with oxidation numbers to determine if any oxidation or reduction is happening for those atoms. But for now, we're just looking at elements and ions, right? So here on aluminum, I have 3 positive, and then on the iron as an element, I have a charge of 0. So going from, and again, trying really hard to make decent arrows here, going from aluminum to aluminum. Oh, the head of that arrow is horrible. This went from 0 to 3 positive. It got more positive, so this is oxidation, right? Poo, more positive oxidation. And then for iron, it went from 3 positive to 0. Well, that's not bad. So that got more negative. This is reduction. So it got reduced. Okay, so now in terms of OAs and RAs, I'm going to use actually the shorthand for this. So iron, because it got reduced, iron 3, this is actually specifically my oxidizing agent. Now, it wasn't the full compound, it was actually specifically just the Fe3 positive aqueous that ended up going through reduction. So that is your oxidizing agent. And if that's like a thing of how do we know that? Well, we're going to go forward with this as time goes on. Don't stress too much about that. If you remember from Chem 20 when we did net and total ionic equations, nitrate is a spectator ion here. It doesn't actually do anything. Well, aluminum, this is a reducing agent, right? So Al solid is my reducing agent because it caused the reduction of iron 3. So the reducing agent goes through oxidation, the oxidizing agent goes through reduction. All right, that is it for basically oxidation, reduction, those redox basics. Once again, kind of talking through a few things, right? When I'm dealing with oxidation, so this is a summary, oxidation is the loss of electrons. So loss of electrons. It happens to the reducing agent, ORA. So it happens to the reducing agent, and in the process, it becomes more positive. So it becomes more positive than it was before. Now, if I take a look at reduction, reduction is the gaining. Right, so it's electrons being gained. It happens to the OA. And it becomes more negative. So negative, reduction, this is my NER. And then oxidation, positive, this is my, oh, that should be a P. My poo or po or whatever you want to say. That is kind of, I think, the best functional way to think about oxidation reduction is the fact that if it's becoming more positive, it's oxidized. If it's becoming more negative, it's reduced. All right, that is it for redox basics. If you have any questions from this, if you need to see more examples, anything like that, write that in the comments in classroom, okay? And then from there we can answer questions and try to work through it. I think actually maybe it might be wise to do one more quick example here to try to help you make sense of this. Let's work with something like if I take a metal and react it with hydrochloric acid. So let's say that I have Zn solid plus HCl aqueous makes for us H2 gas and ZnCl2 aqueous. So if I take a look at zinc, this starts out with a charge of 0. Hydrogen and hydrogen chloride, and again, this is a little bit tricky, but it would be like +1 if we treat it as ionic, and then chloride would be -1. When I look at hydrogen, it's got a charge of 0. Zinc would be +2, and chloride would have a charge of -1. So what's essentially happening here is zinc is becoming more positive, right? It went from 0 for a charge to being an ionic compound where it has a charge of +2. So this went through poo, it went through oxidation because it became more positive. Well, hydrogen went from +1 to 0. Oh, that was such a bad line. So this got reduced, it went through reduction because it became more negative, right? So now if I take a look at what the OA and the RA is, zinc itself is the RA. Well, if I take a look at what the OA is, it's actually only the H positive ion, but that is the OA. So that's actually just the H positive aqueous ion. That is the oxidizing agent. And the reason why is if I look at chloride, it is the same on both sides. You're going to do more work on that kind of thing as we get into half reactions and oxidation numbers. The big thing right now is not understanding, oh, it's just H positive. Being able to recognize, though, that hydrogen ion is what got reduced and zinc is what got oxidized, which means that here I have my OA and then zinc I have my RA. All right, thank you. Have a good rest of your day.